In Chapter 11, we discuss continuous valued channels. Why are we interested in continuous valued channels? In a physical communication system, the input and output of a channel often take continuous real values. In particular, a waveform channel, that is a channel that takes a waveform as the input, is one such that transmission is in continuous time. Therefore, at the physical layer, we need to deal with channels such that the values taken are continuous and transmission is in continuous time. We first discuss discrete-time continuous valued channels. In Chapter 7, we gave two definitions for the discrete channel. In a similar fashion, here we give two definitions of the continuous channel. Definition 11.1 is the first definition. Let fy given x be a conditional PDF defined for all x, where a minus integral fy given x log fy given x dy, where the integration is over the support of y conditioning on x, is finite for all x. A discrete-time continuous channel fy given x is a system with input random variable x and output random variable y, such that y is related to x through fy given x. This is illustrated in the figure. Here, x can have a general distribution, and y always has a continuous distribution. Note that the integral above is precisely the conditional differential entropy hy given x equals a particular value small x, and this conditional differential entropy is required to be finite for all x. Now we give the second definition of the continuous channel. Let alpha be a function that maps r times r to r. That is, it takes two real values and maps it to one real value. And let z be a real random variable called the noise variable. A discrete-time continuous channel specified by the pair alpha comma z is a system with a real input and a real output. For any input random variable x, the noise random variable z is independent of x, and output random variable y is given by y equals alpha of x comma z. This is illustrated in the figure. Definition 11.3 specifies the condition that the continuous channels given by the two definitions are equivalent. Two continuous channels fy given x and alpha comma z are equivalent if for every input distribution fx, the probability that x less than or equal to x and alpha x comma z less than or equal to y, that is the CDF for the input random variable x and output random variable y, when the channel is specified by alpha comma z, is equal to the integral on the right-hand side, which is precisely the CDF of x and y when the channel is specified by the conditional PDF fy given x. And this has to hold for all x and y. So, in definition 11.1, we specified a continuous channel using the conditional PDF fy given x. And in definition 11.2, we specified a continuous channel using the function alpha and the noise variable z. Note that definition 11.2 is more general than definition 11.1 because the former does not require the existence of fy given x. In this chapter, we confine our discussion to channels defined by definition 11.1. That is, we assume that fy given x exists. We now proceed to give the first definition of the continuous memoryless channel, CMC. A CMC fy given x is a sequence of replicas of a generic continuous channel fy given x. These continuous channels are indexed by a discrete time index I, where I is greater than or equal to 1, with the ith channel being available for transmission at time I. Transmission through a channel is assumed to be instantaneous. Let xi and yi be respectively the input and the output of the CMC at time I, and let ti minus denote all the random variables that are generated in the system before xi. It is required that the Markov chain ti minus xi and yi holds, that is, given the input at time I, the output at time I is independent of all the random variables that are generated before xi. Also, the probability that xi is less than or equal to x and yi is less than or equal to y, that is the CDF of xi and yi, is equal to this integral on the right-hand side, which is specified by the conditional PDF fy given x and the input distribution f sub xi. This is an illustration of the continuous memoryless channel 1. We now give the second definition of a CMC. A continuous memoryless channel specified by the pair alpha, z is a sequence of replicates of a generic continuous channel alpha z. The noise variable zi for the transmission at time I is a copy of the generic noise variable z and is independent of the pair xi, ti minus. The output of the CMC at time I is given by yi equals alpha of xi, zi. This is an illustration of CMC2. Let's cop up your real function. An average input constraint for a CMC given by kappa and p, where p is a real number, is the requirement that for any covert x1, x2 up to xn transmitted over the channel, 1 over n times summation I equals 1 up to n, kappa of xi is less than or equal to p. For a fixed value of x, kappa of x can be thought of as the cost for transmitting the symbol x. For example, if kappa of x is equal to x squared, then kappa of x is the energy and p is the power. So the constraint in definition 11.6 says that the average cost for transmitting a symbol is at most equal to p. The capacity of a continuous memoryless channel fy given x with input constraint kappa p is defined as C of p equals the supremum of ixy, where x is the input variable and y is the output variable of the channel, over all input distributions f of x such that the expectation of kappa of x is less than or equal to p. Theorem 11.8 gives the basic property of C of p. It says that C of p is non-decreasing, concave, and left continuous. Here are the ideas of the proof. First of all, C of p being non-decreasing is almost immediate. Second, C of p being concave is a consequence of the concavity of mutual information with respect to the input distribution. And C of p being left continuous is a consequence of the concavity of C of p. It turns out that C of p is also right continuous, and this is also a consequence of concavity, but that requires a separate proof. This property of C of p is not used in this chapter, and so we omit the proof here. We now prove theorem 11.8. First, we show that C of p is non-decreasing. This is seen by noting that in equation 1, the supremum is taken over a larger set for a larger p. Now we prove that C of P is concave. Let J equals 1 and 2. For an input distribution fj of x, denotes the corresponding input and output random variables by xj and yj respectively. Then for any pj, for all epsilon greater than 0, there exists fj of x such that expectation of kappa of xj is less than or equal to pj. And ixj yj is greater than or equal to c of pj minus epsilon. That is, it is possible to make ixj yj arbitrarily close to c of pj. As usual, for lambda between 0 and 1, we let lambda bar equals 1 minus lambda, and define the random variable x sub lambda, which has distribution lambda times f1 of x plus lambda bar times f2 of x. That is, x sub lambda is a mixture of x1 and x2. By the linearity of expectation, we have the expectation of kappa of x sub lambda equals lambda times expectation of kappa of x1 plus lambda bar times the expectation of kappa of x2. This is less than or equal to lambda times p1 plus lambda bar times p2 because the expectation of kappa of xj is less than or equal to pj. By the concavity of mutual information with respect to the input distribution, that is, we fix the channel, we have the mutual information between x sub lambda and y sub lambda greater than or equal to lambda times the mutual information between x1 and y1 plus lambda bar times the mutual information between x2 and y2. This is greater than or equal to lambda times c of p1 minus epsilon plus lambda bar times c of p2 minus epsilon, which is equal to lambda times c of p1 plus lambda bar times c of p2 minus epsilon. Now, the expectation of kappa of x sub lambda is less than or equal to lambda p1 plus lambda bar p2. By the definition of C of P, we have C of lambda times p1 plus lambda bar times p2 greater than or equal to the mutual information between x sub lambda and y sub lambda, which in turn is greater than or equal to lambda times c of p1 plus lambda bar times c of p2 minus epsilon. Letting epsilon tends to 0, we have c of lambda times p1 plus lambda bar times p2 greater than or equal to lambda times c of p1 plus lambda bar times c of p2. This proves that C of P is concave. Now we prove that C of P is left continuous. Let P1 be less than P2, so that P2 is lower bounded by lambda times P1 plus lambda bar times P2. Since we have proved that C of P is non-decreasing, we have C of P2 greater than or equal to C of lambda times P1 plus lambda bar times P2, which in turn is greater than or equal to lambda times C of P1 plus lambda bar times C of P2. Letting lambda goes to 0 in the above, we have C of P2 greater than or equal to the limit as lambda tends to 0, C of lambda times P1 plus lambda bar plus P2 greater than or equal to C of P2. Because as lambda tends to 0, lambda times C of P1 plus lambda bar times C of P2 tends to C of P2. This implies that the limit is equal to C of P2 because the left-hand side and right-hand side above are both equal to C of P2. Hence, we conclude that limit of C of P, as P tends to P2 from below, is equal to C of P2. To see this, we let P equals lambda times P1 plus lambda bar times P2, and so as lambda tends to 0, P tends to P2 from below. This proves that C of P is left continuous.